Welcome to the Public Exam Review for Advanced Math 3200, Unit 5, Chapter 5, Trigonometric Functions and Graphs. In this presentation, we will review the horizontal and vertical translations of the sine and cosine functions. Here we will focus on graphing and transforming sinusoidal functions. We will identify the domain, range, phase shift, period, amplitude, and vertical displacement of sinusoidal functions. And we will graph functions in the form of y equals the sine of x minus c plus d, where c will represent the phase shift of the function and d will represent the vertical displacement. We will also look at the equation for y equals the cosine of theta minus c plus d. In the first example, we will look at the effect of the parameter d on the function y equals the sine of theta plus d. Here we are asked to graph y equals the sine of x plus 2. We can use a mapping rule to represent this new graph. Where xy is mapped onto, we keep x the same and we add 2 to the value of y. Looking at key points from the base graph of y equals the sine of x, we plug in 0, 0 into our mapping rule, and the point 0, 2 will be a point on the new function. As well, we will use the point 90 degrees and 1. Will get mapped onto, you keep x the same, and 1 plus 2 is 3. So the point 90 and 3 will be on the new function. 180 and 0 gets mapped onto 180 and 2. And the point 270 and negative 1 will get mapped onto the point 270 and a positive 1. And the point 360 and 0 gets mapped onto the point 360 and 2. When you connect these points, notice that the base graph of the sine of x has moved up 2 units. Therefore, the vertical displacement is equal to 2. So here the vertical displacement is given by the value of d. And this will affect the equation of the sinusoidal axis. The equation of this new sinusoidal axis will now pass through y equals 2. So to sketch that sinusoidal axis, we go through y equals 2, and that's the central line that passes through the new graph. The pattern for this equation, the pattern for this graph could continue. So at negative 90, we will have the point negative 90 and 1, and negative 180 and 0. So this is what the graph will look like between negative 180 and a positive 360. The period of this function is the length for which one full cycle occurs. And I would just like to highlight that the period of the function does not change as a result of the vertical displacement. So in this case, the period of the function is still going to be 360 degrees, which is the regular period for the base graph of y equals the sine of x. The amplitude is again the distance between the central axis, or the central line, and a maximum or a minimum point on the graph. So in this case here, the amplitude is still equal to 1. So the amplitude here does not change as a result of a vertical displacement. The domain will be all values of x belonging to the set of real numbers. There are no restrictions on x. And the range on this, in this example, is affected as a result of the vertical displacement. Because everything shifts upward by 2 units, we have a maximum value of 3 and a minimum value of 1. So we say there's the minimum value of 1 and a maximum value of 3. So the range are all values of y such that 1 is less than or equal to y, which is less than or equal to 3. And y belongs to the set of real numbers. So as a result here, we have a vertical displacement equal to 2 units upward. And that is also referred to as a vertical translation. A vertical translation upward. When the value of d is less than 0, that will result in a vertical displacement downward. In the next example, we will look at the effect of the parameter c on the equation y equals the cosine of theta minus c. The value of c will represent a phase shift in the base graph of y equals the cosine of x in this example. So here when you see that x was replaced with x minus 2, that will represent a horizontal translation equal to pi over 2 units to the right. A horizontal translation is also referred to as a phase shift. The mapping rule, which will help us to get the new graph, takes xy from the base graph of y equals the cosine of x in this case, and it will get mapped onto x plus pi over 2, and we keep the values of y the same. So for the base graph of y equals the cosine of x, 0, 1 will get mapped onto pi over 2 and 1, which will be the first point on my new graph. Then you had the point pi over 2 and 0. Pi over 2 plus pi over 2 is pi radians and 0. And then you had the point pi and negative 1, which will get mapped onto 3 pi over 2 and negative 1. And then you had the point 3 pi over 2 and 0, which will get mapped onto 2 pi and 0. And then the last key point on the graph of y equals the cosine of x is 2 pi and 1, which will get mapped onto 5 pi over 2 and 1. That point is off our scale, but it would be over here somewhere, thereabouts. So notice that this part of our graph, it's the V-shaped graph, and it's just shifted pi over 2 units to the right. Again, the pattern will continue, so that at 0, we will have the point 0, 0. We will have the point negative pi over 2 and negative 1, and the point negative pi and 0, so that the graph will continue to look like this. All right, but to highlight one full cycle for this transformed function, I will look for the first positive V-shaped part of the graph. So this is the cycle that I'm looking for here, and that gives us the period between that x-coordinate there should be at 5 pi over 2, and notice that the length of the period in this example is still going to be 2 pi radians. So the period did not change as a result of changing the parameter c. It just simply resulted in a phase shift of c units to the right. The amplitude in this case again did not change. The distance between the sinusoidal axis and a maximum point or a minimum point on your graph is still equal to 1. Your domain are all values of x belonging to the set of real numbers, and the range did not change either. So the minimum value of y is at negative 1, is less than or equal to y, which is less than or equal to a positive 1, and y belongs to the set of reals. So what do you expect would happen if c was less than 0? In this example, you had x minus pi over 2. So the value of c was a positive pi over 2, and you had a phase shift to the right of pi over 2 units. So if c is less than 0, that will result in a phase shift of c units to the left. In other words, we have a horizontal translation equal to negative c units to the left. To combine these transformations, let's sketch the graph of y equals the cosine of x plus pi over 2 minus 1 for values of x between a negative 2 pi and a positive 2 pi. So the easiest way to come up with your graph is to use your mapping rule again. So it takes x, y will get mapped onto. This time it will be x minus pi over 2, and the value of y will get mapped onto y minus 1. So when you see the minus 1 here, notice that that represents a vertical displacement of 1 unit downward. So your sinusoidal axis will pass through y equals a negative 1. Let's begin by drawing in that central line. So that line will pass through y equals a negative 1. And that is the equation for the sinusoidal axis. Through y equals a negative 1. So let's substitute. Our base graph is y equals the cosine of x here. So let's plug in some points from the base graph of cosine. So we start off with 0, 1. 0 and 1 will get mapped onto a negative pi over 2 and 0. Then you normally had the point pi over 2 and 0, which will get mapped onto 0 and negative 1. Then you had the point pi and negative 1, which will get mapped onto pi minus pi over 2 is pi over 2, and minus 1 is a negative 2. So pi over 2 and negative 2 will be on the new graph. Then you have 3 pi over 2 and 0, which will get mapped onto 2 pi over 2, which is just pi and negative 1. And then finally, your last point was normally at 2 pi and 1, which will now get mapped onto 3 pi over 2 and 0. So this gives us the V-shaped graph of our new transform function. And again, the pattern will continue for the full cycle. So at 2 pi, the graph will go to negative 1. And then at negative pi, it will go to, at negative pi, it will be back at negative 1. And 3 pi over 2, it's at negative 2. And a negative 2 pi will be back at negative 1. So this will be the full graph for the restricted domain that we were asked to go, between negative 2 pi and a positive 2 pi. But again, the main section of this graph that I want to highlight is this one, between negative pi over 2 and a positive 3 pi over 2. That is the section of the V-shaped graph that I transformed at the beginning. And the period of this function did not change. The distance between negative pi over 2 and 3 pi over 2 is 4 pi over 2, which is still 2 pi radians. The amplitude, again, did not change as a result of a phase shift or a vertical displacement. So the amplitude is still equal to 1. In this case, we were given a restricted domain. The values of x had to be between negative 2 pi and a positive 2 pi, but it's any real number in between. And in this case, the range is affected as a result of the vertical displacement. So the minimum value that y can be is a negative 2. is less than or equal to y, which is less than or equal to 0, and y belongs to the set of real numbers. Remember also that you can determine the equation of your sinusoidal axis and the amplitude using the given formulas. So the maximum value of this function is at 0, plus the minimum value is at -2, divided by 2. So that's equal to a -2 over 2, which is equal to a -1. That gives you the equation of your sinusoidal axis through y equals a -1. As well, the amplitude can be determined by using the formula. The maximum value is 0 minus a -2 divided by 2. That equals a +2 over 2, so the amplitude here is still equal to 1. Let's look at some examples. Here we are asked, what is the minimum value of the function? F of theta is equal to 5 times the sine of theta minus pi over 3 minus 3. In order to determine the minimum value of the function, that's what we need to focus on. So the first thing we need to do is to determine the value of the sinusoidal axis. That value d is equal to a -3, which gives us the equation of the sinusoidal axis through y equals a -3. The number 5 in front here tells us that we have an amplitude equal to 5. So that means then that the maximum value of the function would be determined by taking your sinusoidal axis going through -3 and adding 5 units to it. So the maximum value would be at 2. The minimum value, on the other hand, you take the value of your sinusoidal axis at -3, and you go 5 units below that. So the minimum value of the function is through a -8. Y equals a -8. So that corresponds with Part A in the multiple choice items. In the next example, we are asked, what is the maximum value of the function? But this time, notice that we are given letters here. The function is defined as f of x equals a times the cosine of x plus d. But we are told that a is greater than 0, meaning that a is positive, and d is greater than 0, which means that the equation of the sinusoidal axis is going to move, it will be above the x-axis. So your sinusoidal axis here will be given by y equals d. And knowing that d is positive, it's above the x-axis because the value of d is greater than 0. In the meantime, we still need to look at the amplitude here. The amplitude is equal to a, which means that the maximum value of this function can be determined by taking d as your sinusoidal axis and adding a. And the minimum value of the function is the value of d, and you go a units below. So in this case, we were asked for the maximum value of the function. So the maximum value of the function is given to be d plus a, which is the same as part C, a plus d. In the next example, we are asked, what is the range of the function? So the range of the function, and the function here is defined as f of x equals the sine of 2x minus 2. So here we have the equation of your sinusoidal axis, which is through y equals a -2. The amplitude in this case is still equal to 1. So that means that the maximum value of this function would be given by a -2 plus 1, which is at -1, and a minimum value of the function is a -2 minus 1, which is at -3. So then to determine the range of the function, which is what we are asked for, it will be all values of y such that -3 is less than or equal to y, less than or equal to -1, and y belongs to the set of reals. This answer corresponds with A as the multiple choice item. In example 4, we are asked, what is the phase shift of the sinusoidal function? Y equals a negative 2 times the sine of a negative a half x plus pi over 4 minus 1. We need to work on this part of the equation. By removing a negative a half outside as a common factor, we would be left with x minus pi over 2. Checking that, we can multiply it back through. A negative a half times x is a negative a half x. A negative a half times a negative pi over 2 is a positive pi over 4. So once that is removed, you can see here that the phase shift is equal to pi over 2 units to the right, which represents a horizontal translation of pi over 2 units to the right. This answer corresponds with A. In the next example, which has the same y-intercept as y equals the cosine of theta? The y-intercept for the cosine of theta passes through 0 and 1. If we look at multiple choice part A, you can use a mapping rule to determine the answer for this question. You could take xy from your base graph, and it should get mapped onto, well, in this case it's not x, it's theta, but it would get mapped onto theta, and that would be 5y. So that means that the point 0, 1 will get mapped onto the point 0 and 5. So A is not the correct answer. In the next example, xy would get mapped onto, here we have to take 1/5 of theta and keep y the same. So that means that the point 0, 1 will get mapped onto the point 0, 1. So it appears that B is the correct multiple choice item. If we look at part C, xy will get mapped onto, we take theta and we add 5 and we keep y the same. So the point 0, 1 will get mapped onto 0 plus 5, which is 5 and 1. C is not the correct answer. And for part D, xy will get mapped onto, we keep theta the same, and for y it will be y minus 5. So that means that the point 0, 1 will get mapped onto the point 0 and negative 4. So again, D is not the correct answer. In question number 6, we have which maps the graph of y equals the sine of theta to the graph of g of theta equals the sine of 3 theta minus pi. Again, we have some work to do with g of theta here. It's equal to the sine of, we need to remove 3 as the horizontal stretch factor. So it would be 3 outside of theta minus pi over 3. And then let's check that again. So 3 times theta is 3 theta, and 3 times a minus pi over 3 is a minus pi. So in this case here, we have a mapping rule which takes theta and y from the base graph of the sine of theta, and it will get mapped onto. In this case, it will be 1/3. You take the reciprocal theta, and it would be the opposite of pi over 3 to plus pi over 3, oopsie daisy, and we need to keep y the same. So the mapping rule there corresponds with C as the correct answer. In terms of the functions for functions in the form of y equals the sine of theta minus c plus d, and y equals the cosine of theta minus c plus d, C represents the horizontal phase shift. If C is positive, the base graph of sine or cosine will shift horizontally to the right. If C is less than 0, there will be a phase shift to the left. In terms of the parameter D, if D is positive, your graph will move upward. And if D is negative, your graph will move downward. And that value of D can be determined by using the formula the maximum value plus the minimum value divided by 2, which also represents the equation for the sinusoidal axis. Thank you.